Hello. Yeah, welcome back to Minesweeper Variants 2. Is the music playing? Oh yeah, it is, okay. Alright, well, as you can see here, I have fully completed 10 of each size of the AND, which refers to attachment. And so we're gonna move to combining the plus and the AND to make AND plus combined and attachment, which surprisingly both mean basically the same thing, but are completely different. This is the first time you'll ever get 3 total variants combined with each other, and as you can see here, 2 random rules are combined plus a right side rule is combined with a secondary board, so you get 2 right side rules plus 1 left side rule all together in one board. So let's see how that works, shall we? Alright, hold on, give me a second here. Alright, I'm back. Alright, so how shall we do this? I suppose we'll just start with describing each of these. Okay. So yeah, we'll just start by oh my goodness, we'll just start by describing each of these, I guess. So your left side rule is described on top here, horizontal. While your two right side rules are deviation and liar, and that secondary board there is the liar rule set. Alright, so horizontal. Horizontal refers to the fact that mines may not be isolated horizontally, so it must have something to its left or to its right directly. Deviation means that numbers refer to the 3x3 above it as opposed to around it. So this 3, for example, is referring to these 3 mines. And finally, liar refers to the fact that every row and column has one liar where the number is the number is one more or one less than its actually true value, and you won't know which, but you will know that there is exactly one lie in every row and every column. Okay, so let's start with some very simple logic. In this row, there cannot be mines here or here because they would immediately be isolated, and that will break horizontal. There you go. And one of these are liars, but although we don't know which. This 3 and this 1 is very suspicious. And the reason why is because if you fulfilled this 3 by putting mines here, here, and here, you would immediately fail this 1 because the 1 now sees 2. And if you were to somehow fulfill this 1, then even if you place the mine here, there wouldn't be enough mines to fill the 3. So one of these has to be lying, and that means nothing else in the row can be a liar. Therefore this 0 must be telling the truth, and this 2 must be telling the truth. Okay. Now, I think there must be a liar in one of these 2 cells to finish the row here. But it can't be a liar here. Because if this was a liar, then, well, by definition of what a liar is, it is not a mine. That will make this a liar because this 1 now sees 0. And then you would have 2 liars in the row which fails. Oh, and I guess it would be more correct to mark a liar as a circle. So that means that this can't be a liar, and therefore this is. 1 being a liar is either a 2 or a 0, but now can't be a 2 because there's not enough space, so it must be a 0. This 1 is telling the truth, and therefore the 3 is a liar. 4, oh no, 4 could be telling the truth. Well, 1 is clearly lying, it already sees 2 mines, so 1 is definitely lying. And because it sees 2, it can't see 1 more, otherwise it would see 2 more than its actual value, which isn't possible. 2 is telling the truth here, which is complete. 4 here now can't see 4, so 4 must be a liar. Therefore the last liar is here. 6, wow, okay, well 4 must be a 3 because it can't be a 5. And 6 must be a 5 because it can't be a 7. That leaves us with 2 mines remaining, and each of these mines, as you can see, must have a partner next to it, otherwise they'll be isolated, so 2 remaining mines are here. Awesome, okay. Well, hopefully something like horizontal as a left side rule should be able to help us. I did have a lot of trouble working with the AND for 8x8. As you can see here, I mean, it doesn't really look like anything different here, but yeah, the liar rule set with other rule sets from here actually do get pretty complicated. The starting board always has a lot of numbers in it because you need a lot of things to start off your deductions. But alright, let's keep going. I just love how you have so many letters here. Yeah, see, you have so many numbers. It's more than necessary. Alright, connected. Mines must be connected firstly. All mines must be connected. And secondly, mine regions must be rectangular. So something like this is not rectangular, so it's not allowed. This set of 2 mines is not connected to the rest, so it's not allowed. So rectangular mine regions must be connected diagonally. Okay. Then we have liar and modulo. Modulo means that clues are basically the mod 3 version of the actual clues. This one, which is actually a 7, is still a 1 because 7 is 1 mod 3. 3 is 0 mod 3, so this is a 0. And liar, well, as per usual, liar means every row and column has a liar, but for modulo it's quite different. For modulo, 1 can refer to a 0 or 2, but 2s can only refer to 1s because in this game mode 2 cannot refer to 3 because you can't have a remainder of 3, and 0 can't refer to -1 because you can't have a remainder of -1. So 0s and 2s can only lead you to 1 if they were lying, but 1s could lead you to either 0s or 2s, which is what this thing shows here. Okay, so let's begin. This 2 we know is telling the truth because it's x'd out already. And we know that there must therefore be at least 1 mine here, because if there were no mines here, then this 2 just can't be fulfilled. But the 1 mine here would break this 0 necessarily, because this 0 now can't turn into a multiple of 3. So that means that this isn't a mine. Oh, sorry, this is a liar, which is not a mine. Yeah, it's clearly not a mine. But yeah, because there's at least 1 mine in here, the 0 must be a liar. And that now means that this 2 is firstly telling the truth, this 2 is telling the truth. Well, this can't be a non-mine, because if it were a non-mine, you'd have a mine here and here, and by connected, this would be isolated. So you must have a mine here, which by connected must actually escape out, so that's also a mine. Okay. We don't know whether this or this is a mine. I think either works for now. 0. 0 could be telling the truth, could be lying. If it were lying, it would be a 1, which means that, well, that actually fails. Because if it were a 0, if it were a liar, sorry, then it would actually be a 1, because it can't be a -1. How would that work? We already see 2 mines, and so the only way to actually get to a mod of 1 would be to make it a 4. But by doing that, you're breaking the rule that mines must form a rectangle, because you have this elbow piece here. And so this 0 actually can't be a liar. 0 is telling the truth. And because it is telling the truth, it must be in fact a mod 0, which is 3. So there is 1 mine in here. Okay. I'm not sure if we can get anything out of this. Aha, okay, I get it. This 2 is a liar. Now, I can do something interesting known as the... You know how Minesweeper tricks have these things here, where if these 2 are the same value, then in regular Minesweeper, these are all non-mines. I can use the same trick here. Because these are all mod 3, I can say that instead of there being no mines here, if these were both true, then the number of mines here, or the difference between this clue and this clue, should be 0 mod 3. Because differences still work in modular arithmetic. If you have, say, A mod 3 and B mod 3, and A mod 3 equals B mod 3, so they're both 2 here, then A mod 3 minus B mod 3 is the same as A minus B mod 3, which is 0, because A and B are the same, mod 3. So these should be 0 mod 3. But here you can see that's clearly not possible because it's already mine here, and you can't push the mines in here up to 3. So the number of mines in this rectangle, in this box here, can't be a multiple of 3. And therefore this 2 clearly must be lying. There you go. And now because this is 2 mod 3, this we know is a 1 mod 3 because by liar modulo, 2s can only lead you to 1s, can't lead you to 3s. So there's 2 here. There must be another 2 here. And the reason why is because you must get this to a 1 mod 3. And the only way to do that is to add 2. If you try and add 1, you only get to 0 mod 3. So that's a mine. Whoa, I just double clicked. Okay. Cool. I guess that's cool. Not sure what else we can do though. I suppose there must be some number of mines here. I guess the easier deduction is if this was empty, then whatever mines you have here, because of this 0 having a mine, would be isolated by this thing. So this must always be a mine. And therefore by this 0, which is actually a 1, this can't be a mine. Alright, this 2 is not true, so that's a mine, which means that isn't a mine. And now this 2 is not true, so that's a mine. Okay. Cool. Now Now, okay, we can use a liar again. Every row and column must have one mine, so there must be one mine in this row. Therefore, this 0 is a liar, and this 0 is therefore 1 mod 3. And now how 1 mod 3 would work? Well, I already see 0 mod 3, so it must see a remainder of 1 mod 3. Therefore, this 2, which is kind of truth, can't have both mines in here. I guess a more easy way to say that, if there were both mines in here, you already have a non-rectangular shape. So this 2 must have a mine in here, and 1 mine in one of these cells. And that would actually complete this 0 plus. If you had another mine here, that would push your total up to a 2 mod 3, which isn't possible. So we know that this mine here would complete this 0 plus minus, this 0 liar. So that's not a mine. Aha, now this can't be a mine because if it were, you'd have a non-rectangular piece. This 0 must have a mine here to be completed. And now this must be a liar, and therefore that must be a liar. 1 is a liar, which means it's either 0 or 2. Well, it can't be a 0 because it already sees a mine, so it must be a 2, so that's a liar. There's no need to connect because they already connect. They could connect like this somehow. Yeah, whatever mine you have here does connect this mine to there. So they don't necessarily have to connect by here. Okay, this 2 is a 1 mod 3 because it's a liar. However, it already sees 1 mod 3. So the remaining cells must have a total value of 0 mod 3, which means they're both not mines. Therefore, this is a mine to finish the board. Yeah, because there's 1 mine remaining. Ta-da! Nice. Okay. Wow. Modulo. Okay, the connected did help ease it a lot because there were a lot of easy connected deductions. I don't know about like 8x8s when the connected deductions get like really hard though. Connected is like one of the hardest 8x8s I've had to do so far. But like it does lead some pretty nice looking boards. Alright, let's keep going. Aha, encrypted. Oh geez, area. Dad. Encrypted means that every letter refers to a number, and every number has a letter assigned to it, but it's not given to you just yet. You have to figure it out by solving the puzzle. It's basically just math with variables. What math? It's basically with variables. Okay, so let's begin. Now, oh, I'm sorry, I forgot to describe segment. Segment means that every row must have exactly one consecutive segment of mines. So you can't have mines that are disconnected like this. It's a bit like H, but you also can't have mines. You can't have no mines in each row, because that would be 0 consecutive segments of mine, which is wrong. You must have exactly one. So you can't have disconnected mines. You can't have no mines in each row. Every row must have exactly one horizontal connected set of mines. All right, so let's see how we can do this. Now, my attention is drawn to this dad here. Oh, did I not explain area? Okay, well, sorry. Numbers don't actually refer to the number of mines around them. It refers to area, which is the sum of areas of mine regions around it. So for example, if you had a mine here, if you had a mine here and a mine here and a mine here, then this D would be a 2, because the total area of mines around it is 2. If you had something that looked like this, then this E will be a 4, because the total area of mines around it is a 3 plus a 1, which is a 4. So there you go. To solve this puzzle, which by the way is acronymed C, which is quite nice, I'm drawn to the A and the D, which one of them must be a 1 because they can't both be 0. We see here that every letter has a different number, and every number it has a letter. So they can't both be 0, meaning one of them has to be 1. One of them has to be at least 1, and whichever has to have at least 1 must grow outwards. Right. Now how would that work? They can't both... Yes, they can't both be mines. And the reason why is because whatever region size this thing has, your A and your D would have the same value, which is impossible. So they can't both be empty because these would both be 0 otherwise. They can't both be mines because these would both be the same non-zero value otherwise. So one of these are mines exactly. Now, I can say this is not a mine. And the reason why is because whatever region this E leads you to, this E would touch it. And therefore, it can't continue growing out in an extra area, because then that would cause this value to be higher in some way, which is impossible because they're both E's. And so therefore, this isn't a mine. Nice, okay. Now D. Well, I suppose I can say D is probably not 1. If D was 1, I can do a contradiction. If D was 1, then we'd have to cancel this out. By segment, we have to cancel this out as well. Now, each of these Ds would have to extend out to form a region of size 1. And they would have to close off their regions. And in row 2, you can see here, there's one here and one here, which is not following segment. So D cannot be 1. Can D be 2? Well, if D was 2, then that would happen. Then this D would need to grow out. And yeah, D could in fact be 2. So D being 2 actually does work. But D can't be any greater than 2 because there isn't enough space. So D is in fact just 0 or 3. However, D cannot be 0. Because if D was 0, then by segment you must have at least one mine in row 1. That mine would cause D to no longer be 0. So D just can't be 0. Therefore D is exactly 2. Mines here and here. This 2 is complete. This 2 must go out. This 2 must go out, which, because we know can't see this, because then A will be 2. Can't have a mine here, must go out. A is now a 0 confirmed. And this 2 is complete. Oh, and I guess because we have 4 mines remaining and 4 cells remaining, those are all just mines. And I suppose E is 4. Because yeah, EC is a region of 4. Nice. Alright, well, that's pretty cool. This is also one of the boards with something known as a non-unique secondary board. We know E is equal to 4, but B and C are actually never in the board. So you can see here there is no 1 or 3 in the board at all, and therefore we will never know which B and C refer to. Therefore this leaves us with 2 possible solutions, B1C3 or B3C1, and both are equally valid. Therefore you get a non-unique secondary board, even though the regular board is definitely a unique puzzle. Great. Alright, well this was so fun actually. Let's look at liar and group and cross. Alright, well group is the easiest one. Mines just have to form regions of 4. You can't have regions of 2, you can't have regions of 8, you can't have regions of anything other than 4 in fact. Cross and liar. Well, cross means that numbers refer to how many in one color and how many in the other color. As you can see, there's a checkerboard pattern around it. But it's not given in order. So one could refer to the lights or it could refer to the darks and the other way around. Sorry. Let me think about it. And then liar, well liar just means that okay, well liar, I think I should note that liar just means that for the purpose of cross, one of the 2 values are lies and not both. So this 1, 3 here, you can see, is now a 1, 2. It is not something like a 2, 4. It is not something like a 2, 2. Because not both of them are lies. Only one of them is a lie. And so if you add up both of these numbers together, it'll give you a total number of mines. It would work as a regular liar clue. Same for this 3, 3, which is now a 2, 3. And this 2, 4, which is now a 2, 3. Alright, so let's begin. I think this can't be a mine. If it were a mine, then it must grow outwards to form your region of 4. And in doing that would cause this mine to be a 2, 2, which even if it were a lie would be invalid because both of them are lying. So this can't be a mine. That's fair. What about this? Well, doing this forces it to grow out this way, which would break this 0, 1, which is now a 2, 1. This 0 is increased by a value of 2, which is impossible, so this can't be a mine either. This 1, 2 is clearly lying because you can't have 1 and 2 beside it. And I guess a good trick that we should know for cross is that rather than seeing numbers for what they actually are, you can also see numbers as their sums. This 1, 2 sums to a 3, meaning there must be 3 mines around it, which we know clearly is not possible here, so that's a lie. This 1, 2, therefore, instead of a 3, is actually just a 2, meaning it's either a 0, 2 or a 1, 1. Now, okay, well, firstly, I guess a 2 is much easier to solve here, because if this is a 2, then both of these must be mines. That would complete this 1, 1 as a clue. And this 0, 1, which sees 0, must be a lie, because it would definitely just be 0, 0. This 0, 1 sees 1 here, so it must be a mine. This 0, 1 already sees 0, 1 and is telling the truth, so none of those are mines. Now this must grow outwards, and that is because every mine must form a region of 4. And now 2, 3, how would that work? if 2 3 was telling the truth, you do still have two options. You either have this, which seems to work, because you could have just mines here and here. And do note that there are 8 mines total instead of 10 for this particular variant of group. So you only have 2 sets of 4. But, well, no, that's not true. You could have this happen, and then one of these are mines to complete your region. Yeah, and then the other could just grow outwards, yes. And both are actually possible. So yeah, this could be telling the truth. If it were lying, how would that be possible though? Well, 2 4 is clearly out of the box, because there is no color has 4 empty cells. So 2 4 is definitely out of the box. 2 2 is possible. 1 3 is possible. 3 3 is not possible because you'd have then a region of 6. So it will be 1 3 or 2 2. And I'm not entirely sure which would be right. But alright. Okay, well, I can do a regular group trick here. This can never be a mine. And the reason is because none of these groups are going to be able to reach here. We know that there is exactly 2 groups of mines. And whichever group tries to get here would always have to use more than 4 mines total in its group. So this can never be a mine. There you go, 1 1. Alright. Now, 1 1. Well, this could just be your configuration. And then something like that. That will be useful. That will work. And you can have a lie here. Yeah, that's possible. Oh, I could just do this. Yeah, that's basically identical. What if this was a liar though? Well, this clearly can't be a 1 2, because if it were a 1 2, then all of these are mines, which breaks your group rule being a region of 5. So it can't be 1 2. It would definitely have to be 1 0. And I'm just changing the behind one because both are actually changeable because they're the exact same. 1 0 though. 1 0 is interesting. 1 0 does prevent this from being a mine. Because if it were, you'd have this happen and then this can't actually reach to anything without forming a group of more than 4. This will also be isolated. This is not a mine, therefore, in case of 1 0. Is this a mine? This could be a mine in case of 1 0. Or this could be a mine in the case of 1 0. Okay, so 1 0 is valid, but 1 1 is also valid. I suppose if 1 0 was valid, if 1 1 was valid, sorry, if 1 1 was telling the truth, then this is always a mine because this is the only mine in a colored cell, in a dark cell. Colored, dark. Now this, if lying, would therefore be forced to be 2 2 because it can't now be 1 3. None of these colors have only 1 mine in them. That will force something that looks like this. Now, how does that change things? I'm not entirely sure. Oh, I'm sorry, it's the same trick. This now can't be a mine for the exact same reason. If it were a mine, how would it reach any of these without forming a group of 5? Just can't, so this can't be a mine. There you go, 1 1. Alright. Now, I guess if this was telling the truth, once again, this has to be a mine. Well, okay. One of these are telling the truth. Suppose this was lying. If this was lying, then these are both telling the truth, but that's not possible. Because this 2 3 must have a mine here or here, and this 1 1 is just broken because there's 2 dark mines around it. So this X here just can't be a liar. There you go. So one of these are liars, definitely. Now suppose the 2 3 is a liar, then it's either a 1 2 3 or a 2 2. Now a 1 3 would force to look like... this is not possible. A 1 3 would not work here. And that's because a 1 3 in this set would force to look like this. And now this 1 1 also fails because you can't have a mine in these dark cells. So 1 3 doesn't work here. It would therefore have to be 2 2, which means this isn't a mine. One of these are mines and one of these are mines. If this was a liar. Now, if this was telling the truth, and this 1 1 was a liar, then you'd have 2 mines here for the 2 3 to make 5. And I guess it's 1 1 because it already sees 2 mines, must see 1 more. So it must be a 1 2. Okay, and there you go. Well, in this case, one of them mines has to be here to form a total of 3 because this 2 is actually a 3. Your 1 1 actually is a 1 2 because it now can't be a 1 0. We already know it's 3. And because Oh, it could still be mine here and here, or a mine here and here. Something like that. That's a bit weird. It's a bit hard to guess, I guess. But I suppose we can try and figure out if, say, this was not a liar, it's just telling the truth somehow, or if it was a non-liar. Basically, it could be a mine or it could be telling the truth. Then your liar pattern would just look like this. This is actually not a mine because it's a liar. We know that, and therefore this 1-1 has to be a 1-0 because this 1-1 is a liar, and yeah, clearly this can't be a mine. So this has to be a 1-0. This 2-3 is telling a lie. We know it has to be 1-3. No, so it has to be 2-2, which has to look like this. And this one has to look like this. And you have this. Okay, that works. So I guess it's not that weird. Alright. If this is a mine, if this was empty, then this would happen. This is a line, this is empty. Okay. If this is a mine, could it grow here or here? I guess it could. Okay, what if this was lying and these are both telling the truth? 1-1 telling the truth means there must be a mine here. 2-3 telling the truth means there must be 2 mines in here. I think either one being a mine here works. This 1-1 though, because there are already 2 mines here, must in fact be a 1-2. You would have to have a liar here and a liar here. Ah, that fails. Okay, look at that. That fails. Because suppose this was a liar, right? We know that this is telling the truth. And because it's 1-1, one of these, this has to be a mine. However, looking again, this can't be a liar. Therefore, in this column, well, the liar must be here. Well, that is contradiction, because a liar can't be a mine. A liar has to be an actual value that lies. And so that means this is a contradiction, and by some weird bifurcation rule, this cannot be a liar. It must be telling the truth. Alright, it's telling the truth, which means that in this column, this must be the liar. Cool, so 2-3 is a liar. And therefore, instead of 5, it's probably just a 4. And we know it can't be 1-3 because 1-3 breaks this 1-1 as well. So it must be 2-2. And therefore, there's exactly 1 mine here. That leaves to the fact there's 1 mine here. And because there's already 1 light mine here, this can't be a mine. Great. Alright, this 1-1 could be a liar. If this 1-1 is telling the truth though. If this 1-1 is telling the truth, then you have to have a liar here and a liar here. That will force this to be empty and this to be empty, and this one was just not completable as a truth teller. Because you don't have enough white mines around it. Those are both liars, which are both non-mines. So this one has to be lying. There you go. This 1-1 is lying, which means that it is a 0-1. One of these are mines, we knew that. This 1-3 is lying, it's probably just a 1-2. Yeah, because it can't be 0-3. These can't both be mines to make up your 3. So it must be 1-2, which means that this has to be a mine. Now, okay, well, I guess just by regular group, this has to go up here, which means this happens. 2-3 has to have a mine here. 1-1 is complete, so that's a mine, which means these are both empty. Ta-da! Okay. Yeah, group is a little bit harder to work with in general, I guess. Or maybe it's just cross and liar. Liar is a bit harder than encrypted, I would say, in terms of the attachment thing. Oh well. Okay. Alright, let's keep going. Flowers. Ooh, another checkerboard. Deviation and encrypted. Alright, deviation we know, encrypted we know. It should just feel like regular Minesweeper. Flowers though is a new rule set where every cell in a colored mine, every mine in a colored cell must have exactly one mine in the 4 cells around it. In the 4 cells orthogonally adjacent to it. So you can see here, this colored cell being the lighter cell here has exactly one mine around it. This has exactly one mine around it. This has exactly one mine around it. And this only applies to colored cells. The dark cells can have any number of mines around it, including 0. Mines must have exactly 1 though. So colored mines must have 1. They can't have 0. They can't have 2, 3, or 4, or whatever. But darks can have anything. And apparently this leads to some very flower-looking patterns, I guess. Okay, so let's begin. This CC here is a regular Minesweeper pattern. Just assume there were a wall here. There are some number of mines here which corresponds to C. That will complete this C, which means that this is never a mine. Cool. I can start cancelling stuff off. For example, C can never be 4 because there are only 3 mines here. D could be 4, A could be 4, E could be 4. But could E be 4? If E was 4, then it breaks flowers because this mine here sees 2 non-colored mines. So this E can't be a 4. Now either A is 4 or D is 4. Aha, but D can't be 4 either, because if D was 4, you'd fall into the same problem, where this mine here sees 2 non-colored mines. So D can't be 4, which means A is 4. And if A is 4, these are all just mines. D now has to be at least 2, so we can cancel those out. C. Or C can't be 3, because if C was 3, again, you fall into the exact same problem where this mine sees a lot. So C can't be 3. Can D be 3? Probably could. I think this has to be a mine. And this has to be a mine because whatever mine you see here, D has to see one more mine to make itself up. Therefore, for this D, it sees whatever cells you see here and therefore must see one more mine in total. There you go. Now this can't be a mine because it would break flower. And you have D. Well, D again can't be 4, so it can't both be mines. I guess E now can't be 3, because if E was 3, you'd have the exact same flower problem. I'm guessing D is 3. Yes, because D already sees 3 mines. So D can't be 2. So D is 3. And this 3 is complete. So there you go. This 3. I don't know. C. C could in fact be 2. This works. If C was 1, I guess it also works. E is 1 though, because we already see this E is complete. So E is 1. E is 1. And because C already sees a mine from here, C is not 0, so C is 2. B is 0. We haven't seen B around though. Alright, this 2 is complete. And we can probably just do this with regular Minesweeper. This mine must have a mine next to it by flowers, so that is a mine which completes it. 2 means that's a mine. 3 means one of these are mines, but this can't be a mine because there's more than that will break flowers. So that's a mine. Now this can't be a mine because that'll break flowers, and therefore this is a mine. Ta-da! And I guess I've said this before, but you'll notice in flowers you get a lot of checkerboard patterns. You get a lot of mines in non-colored cells, because non-colored cells have 0 restriction, so it's a lot easier to just stuff mines in there instead. So instead of having flower patterns, you have a lot more diagonal connected patterns. Alright, let's keep going. Oh, bridge. Oh, product. Oh. Alright, BPL. Alright, let's go. How does BPL work? Well, let's start with bridge. Bridge refers to the fact that mines must form 2 bridges in 5x5, 3 for 7x7 and larger. But generally what that just means is that you can see here that 2 bridges refer to 2 mines, one on each end of the board, horizontally, connect to each other via either diagonal connections or horizontal connections. So no vertical connections are allowed. You can have a chain that looks like this, but you can never have a chain that looks like this. This is an invalid chain. But this is valid. So it either connects diagonally forward or horizontally forward. That leads to a pretty interesting implication that every column has 2 mines. In here, in 7x7 it becomes 3. But yeah, okay. As for product and liar, product means that, well, clues represent the product of distances to the nearest 2 mines. So take the nearest 2 mines, take the distances away from it. So this 5, for example, this 10 makes a lot more sense. This mine is a root 2 distance away by Pythagorean theorem. This mine is a root 5 distance away by Pythagorean theorem. Multiply those distances and you get your clue. And this surprisingly does lead to some interesting deductions, even though it at first doesn't seem to give you much. And finally, liar, we know what liar is. Product and liar does lead to some very interesting looking clues though, but we'll see those later. Okay, root 2 must be telling the truth. And the reason why is because if it weren't telling the truth, you would get something that looks like 1 plus root 2 or root 2 minus 1, which are clearly not products here. You can't multiply two distances to give you, you know, some sum. So this 2 must be in fact telling the truth. Okay, bridge. Well, I can say that this root 2 must be a 1 times 2 by regular product, just by regular product, because that's the only way you can have two distances multiplied to root 2. Root 1 by root 2. However, I can do more stuff here. This being a mine never works. If it were a mine, then none of these are mines, because if they were, then these two would be the closest to it, and the product would be just 1, which is not root 2. So these can both be mines, but that does break this mine here, because it can't connect backwards. So how is it going to be part of a bridge? It cannot be part of a bridge. So this can't be a mine. Similarly here would force these to be both be non-mines, and then this can't move forward. So this can't be a mine either. Now 1 and 2, yeah, those can definitely be liars though. Now root 2 must have a mine somewhere. And I suppose this being a mine would be fairly interesting, because that will force your bridge to look somewhat like this. That does fail the 2 though, although we can mark it off as a liar. This 2 could definitely be a liar. And this 1 could definitely tell the truth, yeah. So, yeah, that's definitely possible. You could definitely have a chain there somehow. Okay. If this 1 was a liar, it must be a 2, because they must differ by exactly 1. However, for the 2, how would that work? It would either be 1 by 2 or 2 root 2 by root 2. Yeah, how would a root 2 by root 2 even work here? If you have any mines here at all, they would just entirely take out the entirety of the bottom row. That would render 1 a liar. That would render 2 a liar almost immediately because of these 2 mines here. And I suppose this must be a liar, because there's no liar in a row, which means this must be a mine. It does work. This 1 is telling the truth, which means this must be a mine. That gives you this. This must be empty, which gives you that, which gives you that. Well, I guess not. Okay, well, I guess in contradiction, or on the contrary, if any of these were non-mines, then you can't have any mines here, here, or here. In fact, you can't have any mines here either. Wow, that gives you a lot. For example, this 1 must now be a liar. Okay, so I guess in both cases, can we therefore say that either 1 is a liar or 2 is a liar? I think so. Therefore, this is never a liar. Cool. Doesn't really help much, because not being a liar doesn't tell us much. If it were a liar, then we know it's definitely not a mine. But if we're telling the truth, they could either be telling the truth or it could be a mine. But in either case, you either have 1 being a liar or 2 being a liar. Now, if all of these were empty, then I suppose something interesting. This 2 is telling the truth. This 1 is telling a lie. This 1 is definitely a 2. Could be 1 by 2. Could be root 2 by root 2. This 2 must have a mine here though. So I guess this 1 would therefore be root 2 by root 2. And therefore must see this mine, which gives you something that looks like this. It does give you something like this as well. That breaks a 2 actually. Wait a minute, that just breaks a 2. Because now it sees root 2. Okay, so does that therefore mean that this breaks? It could be actually. So I guess this has to be a liar then. Sorry, this has to be a liar. Wow, I guess I was right. So this 1 being telling the truth must see 1, 1, which means those are both mines. This being a mine now tells you that this must be one of your chains. This can't be a mine because this must be a liar. Therefore, it must go up here. This root 2 already sees something 1 away, so it can't see anything that's 1 away. This 2, well, we don't know if it's a liar or not, but probably is. Can't tell though. This must escape out. No, it doesn't. It's the end of it. It's the end of this chain, so it doesn't have to escape out. We know by regular bridge that these are both non-mines because, oh my goodness, because every column, there you go, that's one of the weird clues. Every column is exactly 2 mines. This clue is definitely a liar. And not only just because there must be a lie in every column, but because 1 by 2 root 2 is just not a valid product. So it must be a liar. Its true value is 2 root 2, by the way. Okay. So its value is 2 root 2. And how does 2 root 2 work? Well, 2 root 2 is either 2 times root 2, or it's 1 times root 8, which is 2 root 2. But clearly 1 by root 8 doesn't work because it already sees something that's 2 away. And root 8 will be further than that. So if it were 1 by root 8, it wouldn't be able to work because it already see this. So it must be 2 by root 2. And being 2 by root 2 would definitely mean that it can't see anything that's 1 away. Root 5, wow. This must continue on, so that must be a mine. This must therefore be a liar. So that's a liar. Okay, 1 by root 2. Right, but this is regular root 2, which means it must be a mine next to it, so that's a liar. Root 5, which is telling the truth, means that it can't see anything that's 1 away. Can't see anything that's 2 away. It probably sees something else that's root 5 away, because it already sees a 1. So that's a mine, which must be true to continue this bridge. So that's a mine. And I suppose this can't be a mine, because if it were a mine, that would just be a regular 2. It also can't be a mine by bridge, because it can't go backwards. 2 root 5. 2 root 5 is either 2 times root 5 or 1 times root 20. Clearly 1 times root 20 doesn't work here because it already sees things root 5 away. So it must be 2 by root 5, so this can't be a mine. Therefore that's a mine to finish the bridge and the puzzle. There you go. Nice, we got 2 chains here. 1 chain here and 1 chain here. And this is a diagonal connection. There you go. Very sweet. Very cool puzzle. Alright, do we have time? I think we have time for like exactly 1 more puzzle. Oof, cross and encrypted, but also triplet. Actually, triplet does happen to be the last of the left side variants, so I guess this is a good place to end it off. Now, triplet means that, firstly, mines can't form rows of 3, vertically or horizontally. Diagonals are free game though. Non-mines also have the same restriction, so non-mines come from rows of 3, diagonally or vertically. I'm so sorry. Diagonally or vertically. Diagonals are also free game though. So it's a bit like triplet in the main game, in the first game, except diagonals are not counted. And empties are also counted. And then you have cross and encrypted, which did show up before, so there you go. Now B and C just can't be 4, because B and C are both at most 3. C and C. C and C. Well, I mean, just by regular triplet, these have to both be mines, and that's because these can both be empty. Otherwise, you know, you'd have a row of 3. So these are both mines. I mean, really no one of them had to be a 1. I guess C now must be at least 1, because whichever looks at the light source is just C. How is this a thing though? Like what? Well, I know C is 1, but no, wait, hold on. Lights can't be 0. The reason why is if lights were 0, then these are both empty. Which means light also has to be at least 1. And if lights are at least 1 and darks are at least 1, then both of them have to be at least 1. Therefore B can't be 0. Alright, cool. Great. Now BC can't be 2, 3. If it were 2, 3, then these will both be mines, which will give you a full column. So one of these are at least 1. One of these are 1s. Now I do note that none of these numbers can give you a value of 2 total. If they give you a value of 2 total, then think about it. In a regular 3x3, to ensure that there are no empties, 3x3 empties in every row must have at least 1 mine. Because if a row did not have a mine, then it would just form a triplet. It would break triplet. Therefore, every row must have at least 1 mine. By that logic, this 3x3 here must have at least 3 mines. And therefore, this value can't have a total value of 2. Can't have a value of 2 or less, basically. And therefore, C can't be equal to 1. If it were equal to 1, you have a value of 2, and that will break triplet. So C can't be 1. C is at least 2. However, B therefore can't be 3. If B was 3, that will force C to be 2, and we already know that BC can't be 2, 3, because that will give you mines here and here. So B can't be 3. If C was 3, then B must be 1, because again, BC can be 2, 3. that would give you something that looks like this, which is valid so far. C being a 3 though is fairly interesting, and I guess yeah, C being 3 doesn't work actually, because if C was 3, you'd have a total value of 6 here, right? Or I guess a slightly easier way to explain it is, if your C was 3, then the lights must be 3 firstly, so those are both mines. The darks must be 3, but notice that either these are both mines, or these are both mines. Because even if you only placed one mine in the other cell, you can't place only one mine in this set as well. So one of these sets had to have 2 mines in them, and whichever set has 2 mines in it will form your row of 3. So C can't be 3, which means C is 2, B is 1. Okay, so 2, 2 over here. I guess you have 1 mine in here. Not sure how that helps. That will give 1 for this 1 too. Which means now you either have a mine here or you have a mine here. Not sure though. This 1, 2. If this were a mine, then this is empty, which means one of these are mines, which is fine. Or you could have this being empty and then I guess some of these being mines. Yeah, that doesn't really help much. Oh, hold on. No, this 1, 2. You can't have a mine here. Because if you did have a mine here, then these would both be empty, which would form your 3 in a row. So these are both non-mines. Ta-da, okay. This must be a mine now. And if this being a mine means that this is empty. Now these are both mines for triplet. This 1, 2 is complete. This 2, 2 is going to be complete. Because there's 1 mine here. 1, 2. Well, one of these has to be mines for your triplet. So this isn't a mine, which means this is a mine. I mean, by regular triplet, this is a mine as well, which means that these are both non-mines. Oh, if I have another letter. Okay, 1, 2 means that these are all just mines. This is not a mine by regular Minesweeper, by regular triplet, sorry. And 1E, well, 1 is referring to this definitely. So E we know is definitely already at least 2, so E can't be 0. E can't be 4 either because darks do not have 4 cells, so E is exactly 3, meaning that's a mine. 1 is complete, so that's not a mine. 1, 2 means these are both mines, and 1, 2 here is complete, so that's not a mine. There you go. We have another unsolvable board. Because you either have this is a liar and this is a liar or the other way. Liar? What? No, this is a A is 0, D is 4 the other way around. So ta-da! There you go. Triplet cross encrypted. Okay, well, that was fun. We went through all possible left side variants, which is something that usually never happens. But there you go. That was pretty fun. Alright, well, I'm gonna try getting through combine attached, probably by the end of this week or something. And then I'll continue on doing hashtag. And hashtag is basically the same as hashtag in the normal game. So that shouldn't be too much of a difference. And then after that, we'll go to the plus hashtag, which does not include end. But could you imagine plus end and hashtag? That would be really, really crazy. Oh well, okay, I guess end and hashtag actually aren't compatible with each other. But you'll see why next week. Alright, well, hope you had fun. Hope you enjoyed this video. I'll see you guys next time. Bye bye.